Yeah.
It's about significant figures. So trailing zeros are insignificant.
Correct.
But if there's a decimal point like that,
Then they would be.
so all of them are?
Yeah, so now they all are significant.
Okay.
Yeah. All right, let's go ahead and get started. So I wanted to go back and do the periodic trends in more detail, since we kind of rushed those on our last lecture. So let's look at those trends again. So we had looked at ionization energy, and so I'll just define that again. Actually, before we get started, are there any questions or anything? So we have lab today. So we'll be doing lab 2 for everyone in person. And I just posted Lab 2 to grade scope, so you can turn those in there. And then don't forget, Earth Day celebration is this Friday. Well, Earth Day is this Friday, and we'll have our celebration. So it will be on both the Riverside and Redwood campuses. So tell your friends.
What are they doing for celebration?
So there will be like some local representatives from different organizations that do like conservation efforts. So it depends on campus. We might have a few chemistry students present like sustainability topics, and then there'll also be pizza, and we'll also have like little seeds and dirt for people to make like mini pots basically with newspaper or paper, and then you can go, stick those in soil and it'll decompose. So come check it out, should be fun. Ordering lots of pizza for that. All right, so let's go back to trends. And so we had kind of rushed this ionization energy, which just basically says we have some generic metal plus our ionization energy gives us a cation plus some electron that was ejected. And so we looked at that trend. And so we had said, and this should be a recap, and so I'll kind of simplify this. So ionization energy increases as you go across the periodic table, aka it takes more energy to eject those electrons, right, as you fill up this shell. And we can see that, and let's just take, boron versus fluorine. So boron has its p orbital, its s versus our fluorine. And so boron is in group 3, so 3 valence electrons. So we fill up 2 in the s first, 1 in the p. And so you can kind of tell that boron would have, it's pretty favorable to eject this 1 electron since it just has 1 electron in the p. Versus fluorine, right? So fluorine is in group 7 over here. So you can write a nice 7 over there to remind you it has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. And so that's really close to that octet. So this is unfavorable, right, to try to knock off one of those electrons. So that was ionization energy. And then we also, kind of related to ionization energy is electron affinity. So let's look at, so there's both electron affinity and also electron negativity. All of those are pretty related to ionization energy. So there's slight differences in electron affinity versus electronegativity. So electronegativity is based off of values in a compound. So basically you take a compound and see which atom is kind of pulling more electrons towards it. And so the most electronegative element is fluorine, and that also will help you remember your trend. So similar to ionization energy, you have increasing electron negativity as you go across and also up the periodic table. So that, again, goes back to this basic principle that elements up here, the electrons are closer to the nucleus, and so those really, really want those electrons versus, let's say, fluorine versus iodine, where the iodine has a greater radius. And then electron affinity is a little bit different in that it's measured in the gas phase. So basically, electronegativity would be in a compound versus electron affinity, which is basically metal plus an electron gives you a negatively charged anion here. And so again, this is a gas phase measurement. They follow almost the exact same trend. There's just a weird, actually, discrepancy where chlorine has a higher electron affinity than fluorine. But I think that's one of the few anomalies in the trend, and probably that has to do with just chlorine has a larger radius, so you can kind of hold that negative charge just a little bit better than that fluorine in the gas state. And let's see, so what other trends should we talk about? So we mentioned atomic radius from last time, so I'll just re-mention it again. So atomic radius increases that way, and so it might be kind of funny because, again, these elements have a larger radius, but that all goes back to our orbitals. So as we fill in our orbitals with more electrons, now that's holding it tighter to the nucleus. So the nucleus, of course, is positively charged with protons, right? Our electrons are all negative. And so if they're still on that same energy level, that's going to cause it to hold it closer. And then, so we also, kind of the last trend, I guess, we'll look at is metallic character. And so that also follows this general trend of increasing as we go from right to left and also down. But you can kind of gather that from just our little key here. So we saw, right, that these elements over here are gases. These are kind of more, non-metals and nice compounds. And then all these, right, were metallic, shiny, all classic kind of metals. And you can see that reflected again in your periodic table. So over here, right, you have your metalloids, which is your stair-step kind of transition. And then you go to metals, transition metals, and all the rest. All right, so I think we covered periodic trends now. So now we can go back to chapter 3. And so chapter 3 is now looking at chemical bonds. And so how do compounds, make bonds, form bonds? This is really important. And so chemical bonds result from the attractions between the charged particles, so the electrons and protons that compose the atoms. And so there's 3 main types of bonds, but we'll focus on ionic and covalent. So we'll look at what ionic means, what covalent means. And then metallic is kind of special, so this would just be like metals or metal alloys. But these are typically considered to be bonded by a sea of electrons. So we'll kind of ignore that metallic bonding for now. So now we want to look at, well, what is an ionic bond versus what is a covalent bond? And so we can look at it in this picture here. So we look at our ionic bond. So you kind of notice it's in this crystal structure. And so what's distinct is ions have some sort of cation, which is some positively charged ions, in this case sodium. And then they have some sort of anion component. And they're in the correct ratios such that the overall salt is neutral. But then if you notice, right, there's no bond between them. They're just alternating, stacked together in this crystal structure. And so we'll find that there's no bonds, so no sharing of electrons. They're just held together by those electrostatic forces. And so other distinct characteristics of ionic bonds is they're always a metal plus a nonmetal. And so we'll look at that, what that looks like on the periodic table. And this will be compared to covalent bonding. And so covalent bonds are distinct in that you have actual sharing of electrons. So I'm just drawing out water here for a second. And so oxygen has right? 1, 2, 3, 4, 5, 6 electrons that it brings to the table. Each hydrogen brings 2, and so oxygen and hydrogen are sharing those 2 electrons there to make a bond. All right, so let's look at this in more detail. And watching the chat too, so again, just make sure, ask your questions as they come in. So again, an ionic bond occurs between metals and nonmetals. So I typically say, group 1 or 2, sometimes 3, and then, plus some sort of group 7, 6, 5. And so we look at our periodic table. So these are all our metals here. So we're kind of ignoring transition metals, so they would be included as well in our ionic compounds. So all these, so transition metals plus anything on this right side over here gives you an ionic compound. And so again, what makes the ionic bond distinct is that it involves a transfer of electrons from one atom to another. So again, they're not sharing, they actually transfer over. And so the metal, we'll see that it becomes the cation as it donates an electron, and then the nonmetal becomes the anion. So let's look at this in more detail. And so we have sodium chloride. So let's just start by drawing our Lewis dot structures for each of these. So we have sodium. So how many valence electrons does sodium have? So 1, so exactly, it's over here. So again, write a big 1 or whatever you need to do to remind yourself. So I'll just draw our little 1 electron there. And then we have chlorine. So how many valence electrons does chlorine have?
No, 7.
Yeah, 7. So good, so it's over here, again with group 7. So we can draw in our electrons. And so right now, right, we're noticing, so sodium is, let's go back over here. So sodium, if we're looking at its electron configuration, so it has an electron in the 3s1 shell. But if it just lost 1 electron, right, it would have the same electron configuration as neon. It would have 8 electrons. It would be satisfied by the octet rule and be happy. And so meanwhile, right, chlorine is just 1 electron away from that noble gas configuration of argon there. So what's going to happen is that sodium is going to lose an electron. So it'll become sodium plus. And we have this 1 electron. And so this electron then will go over to chlorine, so plus our electron from sodium. And so we'll make our chloride anion here. And so I just drew now the appropriate Lewis dot structure. So of course sodium lost its 1 electron. So we can just draw it like this, sodium, and then you want to put a plus charge on there to signify that it lost that 1 electron. And then chlorine, of course, fill in all 8. So now it has 8 valence electrons, and now it has a negative charge. So the other thing that you notice is our charges are balanced, right? So sodium, you have 1 equivalent of sodium for every 1 equivalent of chlorine. And then so if you look at your fancy periodic table that I gave you, so it also has some charges and signs on there. And so remember, these plus signs are those oxidation states. So those oxidation states are telling you what it tends to do. So in this case, we have group 1, 1 valence electron, and then it probably says like a bunch of 1 pluses all on there. And so that's just telling you that those metals have a tendency to lose that 1 electron, so they give it up very readily and then donate it to whatever nonmetal. And then so group 7, they probably have a bunch of charges of -1, so signifying that they like to be in the -1 oxidation state and gain an electron. So then when we write out these formulas, we just want to make sure that our charges balance, and then we can just write it as sodium chloride there. And so again, now we have these oppositely charged ions, so our cation and our anion, that attract one another by electrostatic forces and form an ionic bond. And so the result is this ionic compound, which is in the solid phase, and it's in this lattice structure. So this is just referred to as its structure, so it's 3D array of atoms, so how the cations and anions kind of stack together. And this, of course, depends on the radius and the charges, how exactly they fit. And then so zooming in on just this little schematic, it gives us, again, just a play-by-play of how this happens. And so this would be a pretty nasty way to make sodium chloride, but you could do it so you could take, sodium metal, react it with chlorine gas. So again, we saw that electron transfer giving us our sodium cations and chloride anions. All right, so we've kind of covered this. So there was a reason why I was cramming in Lewis theory and in with our electron counting. So this Lewis model helps us kind of understand who we're looking at and what's going on. So again, in this case now we're looking up potassium. Here's its electron configuration. So of course, we know that potassium is in our group 1. All these have a trend of something in the NS1 energy level. So of course, in this case, a 4s1 would be our valence electrons. And then that is the one that is lost, goes off to the nonmetal, and then leaving us with an octet. So in this case, potassium is satisfied by a full octet in the 3 shell. So now this periodic table just kind of emphasizes the different oxidation states. So like we were saying, we should have a 1+ oxidation state for these alkali metals since they tend to lose 1 electron. Then the alkali earth, again, those were NS2 for their electron configuration. So that means they tend to lose those 2 electrons now. So they have a 2+, for that 2+ oxidation state that they tend to be in. And then group 3 can be a little funny, so that's why they just put aluminum here. These just signify, so kind of the other issue is the transition metals have variable oxidation states. And so we'll get into a little bit later how to determine what the charge is. But if you look at your periodic table and look at the transition metals, they probably say all sorts of funky numbers on there, like 3 and 2 and 4 and 5 or whatever.
Iron has 2, 3, and 6.
Yeah, and those are just the common ones. So you'll find that metals can take a lot of oxidation states. So they just list kind of the most common ones there, but really the transition metals can be kind of anything. And then it just points out, so scandium and yttrium, these tend to be in the 3+ oxidation state. So if you see a compound with them, you can kind of have a heads up there. And then, of course, looking at our anion side now, so we see our halogens, right? Those all have a -1 oxidation state. Our group 6, all those are -2 oxidation state. And then we get some oddities starting in group 5. So they tend to mainly be -3, but you probably can read on your periodic table that they're also +5 and can do other funky things. And so again, ionic compounds are composed of the cations plus our anions held together by an ionic bond. So some other examples of ionic compounds. So sodium bromide, that's a pretty obvious one. And then we'll look at some of these other compounds in more detail. So I want to point out, so we have aluminum carbonate. So aluminum carbonate. And so it's kind of tricky about these ones, and we haven't introduced it yet, is that this is a polyatomic ion, which means that the CO3 is held together by covalent bonds, but the aluminum and the carbonates both have charges. So if we were to kind of separate this out, so we have aluminum. Oh, I knew I screwed up something. There we go. So aluminum, so we have 2 equivalents of aluminum. So both of those have a 3+ charge. And then versus our carbonate, so let me draw out just kind of one representative structure of carbonate. And so carbonate itself has a -2 charge. And again, you wouldn't know this unless we were talking about it and looking at a chart. But again, we'll cover that. We'll get there. And so since this whole carbonate has a overall 2- charge, right, we need to balance this overall 6+ charge. So that's why in the formula, you notice there are 3 carbonate units. And so if you were to put this in solution, so the other thing about ionic compounds is that they dissociate in solution. So you could take this aluminum carbonate, right, put it in water, and then it would dissociate to make 2 equivalents of aluminum and then 3 of our carbonate. So that's what that would kind of look like in solution. And so same with these, so we have calcium hypophosphate, magnesium sulfate, so those again are polyatomics. And so the important part is the basic unit of an ionic compound is called the formula unit, and this just means that this is the smallest electrically neutral collection of ions. So just like we saw with sodium chloride, right, they would be in a 1-to-1 ratio. And so in a chemical formula, the sum of the charges of the positive ions must equal the sum of the charges of the negative ions. And so just for practice, so what is the formula for a compound of magnesium and nitrogen? So take a minute or two. How would you balance those charges? What are the oxidation states? looking in the chat for answers. So let's just start. What's the oxidation state of magnesium?
+2.
So +2. I'm just kind of writing how I would approach this with scratch work. So magnesium, right, 2 plus. And then, so what's the oxidation state of nitrogen?
+5, +3, or -3.
So which one would be a good choice? So we have a,
-3.
so let's go with -3 since we're pairing it with another metal here. And so there's an easy way to do it called the swap trick. So basically, right, you just take this 2, it becomes your little subscript for the nitrogen, take this 3, becomes a subscript for magnesium. So you should have gotten magnesium 3 and 2 there. And then you can see how the charges balance out. So you have 2 plus for magnesium times 3 of them plus your -3 charge from nitrogen times 2 of them, and that cancels out to give you 0, which they didn't indicate that there is a charge on this, so we assume it is neutral. So sometimes you may have like a charged compound, and in which case it would indicate so, and then your charge would have to equal to whatever that total charge is. So now let's see how we name these ionic compounds. And so ionic compounds can be categorized into 2 different types depending on our metal. So we have our metals that form only one type of ion, aka only one oxidation state. So again, those are going to be, and it lists them here, so your alkali metals, right, those are all 1+ oxidation state. Your alkali earths, so those are all 2+. And then it lists some typical metals, and so I might write these down somewhere. So zinc is always in the 2+ oxidation state. It's important to point out since it's over here in our transition metal mess. Then aluminum, we discussed that, so that tends to always be 3+. And then silver is another interesting one. So that is always in the 1+ oxidation state. So I would highlight that, star it somewhere, so you know if I see a silver compound, it has to be in the 1+ oxidation state, and I don't need to indicate its oxidation state. So this is fairly straightforward. And then the other type is that we have metals, right, that form more than one type of ion. So that's where we mention the transition metals are mainly to blame. But then there are also some p-block metals that tend to have 2 oxidation states. So they should be marked on your periodic table, but they tend to be tin and lead are the main ones that come up. So tin and lead either tend to be in the 2+ or 4+ oxidation state. And then now I realize I didn't put how to name them. Oh no, here we go. So let's start with how to name these kind of basic ones. So how to name, question in the chat, is there a way to get a printed copy of the periodic table? I think I posted it last lecture, a link to it, but if you see me in person or email me, we can arrange a way to get a printed copy. And so to name these, how we name them is we just name our metal. So looking at sodium, right, we just name the metal, so sodium. And then plus our anion ending, but you change the ending to "-ide". And so in this case, right? We had chlorine, so now chlorine becomes chloride, and we have here, so sodium chloride. So take a minute or two, and so see if you can name these next ones. So MgO, CaF2, Al2O3. And then I'll post a link to the periodic table again over here so you can find it. So what do we get for this first one?
Magnesium oxide?
So magnesium oxide, and I see it in the chat too, so excellent. What about the next one? So calcium, and then what'd you say? Oh, so in this case, so you don't have to indicate how many, so you just say fluoride. And that's because with ionic compounds, right, you know what the formula is going to be based off of the charges. So if you are looking at the name calcium fluoride, you have to kind of look, all right, calcium's, 2+. I know fluorine or fluoride has a -1 charge. Oh, that means, right, I'm going to need 2 fluorides then to balance that. And so I don't want to ignore this question, but I saw it, and it says, like, in the chat, do you just end up picking the charge that works best? So it kind of depends what you mean by that. So going back to like this example, for instance, in this case, right, nitrogen had a bunch of kind of positive oxidation states, which didn't make sense because it's paired with a metal. So in this case, it had to take a negative oxidation state. But then we'll address your question for like the other ones, so kind of for those variable oxidation states, how you determine what's the charge. And then, so what about this last one, Al2O3? So aluminum oxide, exactly. And then, so same thing, so for this one, right, we know we could go back and forth. So looking at the name, okay, we have aluminum. I know that's always in the 3+ oxidation state. We can look at oxide. Oxygen's always in the 2-. And then use our little swap trick here for ease of math. And so that gives us back our formula. And so now this is just more oxidation states. Let's see. Trying to think if there's anything significant to point out. So even though these only have one oxidation state listed, they can definitely take more than one oxidation state. Just don't let that throw you off. Again, maybe highlight zinc since that does only have one oxidation state, and also highlight silver. So those ones, again, only have one oxidation state, so we don't.
Silver has 3.
So most commonly, we just look at the one.
Oh, sorry.
Yeah.
I was confused.
Yeah, they can do all sorts of funny things, but for purposes of naming, silver is always considered to be 1+, at least in our scenarios. All right, so now let's kind of get to the other question. Well, how do we name the other type that have multiple charges and we don't know what the charge can be? So again, their charge cannot be predicted, as in the case of most elements, and so it must be noted in their name. And so what's really nice, and let's skip down. So even back when I learned chemistry, which wasn't that long ago, but it's getting longer, every year that I teach this. So we had what's called this older naming system, and it was kind of a pain in some regards. So if you notice, and if you ever run across this, you can at least know where it came from. And so the lower oxidation state was always given this ose ending. So in chromium, you have your 2 most common oxidation states, so 2+ and 3+, so you used to have to call it chromous and chromic. You usually see this for iron compounds still a lot, especially if you're looking at an old bottle of compounds. So you see ferric chloride, so that would be FeCl3 to indicate that iron's in that oxidation state. But lucky for y'all, so we don't do this older naming anymore. So all we have to do is name our metal, and then we indicate the oxidation state in parentheses here using Roman numerals. So a lot easier, no crazy memorizing anything, so super easy. So let's go back. So looking at this case for iron, so iron can form a 2+ cation. It could also be 3+, or many other things under the sun. And so in this case, right, we have to be able to distinguish between these 2 iron sulfate compounds, right? So you can't just say iron sulfate. So to help you guys write this SO4, this would have an overall 2- charge. So this is called sulfate, a whole polyatomic ion. But again, right, we don't know what ratio it is. So to name it, so for this one, if we're looking at FeSO4, so we would have to look at our anion. So in this case, again, I gave it to you that this SO4, this whole thing, is 2-. And then so if this is a -2 charge, we know they're in, right, a 1-to-1 ratio. So what has to be the charge on iron? So 2+, exactly. So we know that iron is in the 2+ oxidation state. So when we go to name it, now we can name iron, and then our Roman numeral 2 for our 2+, and then sulfate. And then so comparing that with our other potential formula, so we were given Fe2 SO4 3, and so you could kind of do the reverse of your swap trick. So in this case, if you did the swap trick, you would get Fe2, SO4, you could tell, right, they're in a 2-to-2 ratio. That simplifies to 1-to-1. And then, so in this case, you can back it out. And does that work out? And so, yes, that works. So our sulfate, it is 2 minus. And so now we see if we have -2 times 3 of that, of course, that gives us an overall -6 charge that we need to balance out. So since we have 2 irons here, indicated by our subscript, it has to be in the 3+ oxidation state. And so we can just name it iron. Now 3 for, again, the 3+ oxidation state, and then sulfate. Oh, and then, so make it note, so I mentioned lead and tin, but I forgot thallium. So thallium tends to form different cations as well. If I remember, thallium tends to be either the 1+ or 3+ oxidation state. I'm sure your periodic table indicates that. All right, so once again, right, our charge goes in parentheses, so, highlight that, whatever you need to do. So it indicates the charge, right? Not how many or anything. It's the charge, it's the oxidation state. So for example, again, copper 2+, we can just indicate that by writing copper 2 in Roman numerals versus copper 1+, where we just write a 1 there. And then, so now we have our basic naming scheme again. So again, just our name of our metal, the charge now for our variable oxidation state metals in Roman numerals, and then again our base plus changing the ending to "ide" again. So take a minute or two, look through these 4 examples. So how would you name them? You have a question or answers?
So would it be iron 2 chloride, or would it be iron 2 dichloride? Or just iron dichloride?
So it'd be, so for this first one, so iron 2, right, and then just chloride. So you don't want to use the prefixes or anything. So that's for covalent compounds. So again, we don't need to indicate kind of how many, because we have that indicated with our oxidation state. So if we name it like this, what is going on? I don't know why it's doing that. That's annoying. So by naming it like this, right, we say iron 2, so I know, okay, iron is in the 2+ oxidation state. I have chloride. I know that's always in the -1 oxidation state. And then we can do our little swap trick and get back at our formula there. All right, so what would be the next one? FeCl3. So iron 3 chloride, exactly. Again, we don't need to indicate how many. We can tell that just by our oxidation state. And I see it in the chat too, iron 3 chloride, excellent.
Wait, would chloride have to be indicated since it has several different states it can be, or?
No, so chloride always just takes the 1 minus. So your periodic table is very thorough, so it lists like a bunch of other things on there.
Okay,
And-
so it can be, say, +7, it's just not for these bonds, or it's not very common.
Yeah, so that would be more if like chlorine was acting as a covalent compound, and then it
Okay.
would like formally take on those oxidation states. But
That makes sense.
yeah, there's like no perfect periodic table.
Why not a periodic table that just has literally every piece of information on it?
Yeah, that's my goal with that one, is it has a lot of information, but almost too much sometimes. What about this next one? So SnO2. So try that one again. So I like the tin. So if we had written tin 2 oxide, right, that would tell me tin is in the 2 plus oxidation state, right? Oxygen is in the 2 minus. So those balance, but does that match?
No. Oh, tin.
So use your oxygen to help you. So I see some guesses. Exactly, 4. So we have to look at our oxygen. And so oxygen is always, always, always in the -2 oxidation state. And so this is where kind of backing it out can lead you a little astray. But if you were to, let's say you were doing the reverse swap trick, right? You get 2, and then you get 1 over there. But then if you look, well, oxygen's not -1 for its oxidation state. So we kind of have to multiply everything times 2. And okay. And however way you want to do it, so some of you may like it more algebraically, and some of you can just see, right, okay, I have -2 for my oxygen, times 2 of them, so that gives me -4. So this has to be 4 plus. And so that would be tin 4 oxide then. And so just as kind of, again, watching out for pitfalls. Make some space here. So if you reverse back this tin oxide, so we have 4 plus, oxygen, 2 minus, right? Do our little swap trick to make things easy. Right, so that would give you a 4, that gives you a 2. But what do you notice about a 2 and 4? And that kind of explains how we got back to our original formula, right? Because we want to write these in kind of the lowest ratios. And then 2 and 4 share, right, a least common multiple of 2. So if you divide everything by 2, you get back 10O2, which was what they gave us originally. So we just are looking for, right, the lowest ratios for the formula there. So just kind of watch those as you do the swap trick kind of back and forth. Kind of make sure your oxidation states work out, and then again you have your numbers simplified to the smallest ratios. All right, last one, CON. How would you write that?
Cobalt 1 nitrogen.
No.
No, I don't see it as cobalt.
So I like cobalt. And then, but what's nitrogen's oxidation state? So, yeah, I like -3. So it's over here in that odd category, where again, it's like that 3 minus, 5 plus type of scenario. But we have our cation from cobalt, so that's our positive charge. So we kind of have to pick, right, the most reasonable negative oxidation state for nitrogen. So that's 3 minus. So what does that give us for our compound name?
Cobalt 2 nitrate, no, nitride,
So I like nitride, but then what's the,
3.
yeah, so cobalt 3 and then nitride. And then I threw nitride in there because for some reason, like, people look at nitride and blank out or start writing any other weird combinations of nitrogen compounds. So just look for that. There's also, if I had picked cobalt AS, so that's just arsenide.
Where's AS?
So-
Arsenic, ooh.
Yeah.
Arsenide.
Yeah, so that's just, it's a naming thing. For some reason, those tend to throw people. And then I see it in the chat, cobalt 3 nitride, so good job with that one. Any questions so far on naming? All right, so I probably should have printed a polyatomic sheet. I'll have to do that for next time. And so we have all these polyatomic ions, so now how do we name them? So it's kind of the same thing, except we'll name either our cation, which is usually a metal, and then plus our, whatever our polyatomic, or vice versa. So the only positively charged polyatomic is going to be ammonium, and then everything else has a negative charge. And so if you look, and so this is why I need to give you a handout of this, or, you know, you guys have your internet, computers, whatever, so you can Google like common polyatomic ions. And so basically, all right, you just want to be able to recognize them. I'll point out kind of the few common ones. So there's hydroxide comes up a lot. There's good old carbonate. There's sulfite, but sulfate is more common. So notice sulfite is just missing an oxygen. Let's see what else is common. I just want to point out peroxides. So, right, I made a big deal that oxygen is always, always, always in the -2 state. So the only exception is peroxides. So notice it's O2 with a -2 on there. So each oxygen has a -1 oxidation state. So anytime you see like a peroxide, that is the only time where oxygen would be in like a -1 oxidation state. And then if you ever see acetate, so acetates tend to confuse people just because, A, there's two different ways to write them. So you have, yeah, C2H3O2 minus, or sometimes it's written like this Jew, so CH3COO. So just kind of watch out for this. It's relatively common. And then, so nitrate will come up a lot. Let's see. Oh, and then phosphates are really common, so that's PO4 with a 3- charge. And of course, the rest you can kind of read for yourself.
Ammonium. How do you pronounce
Which one? So these?
Disulfate? S2O3.
Yeah, so this is thiosulfate. And then you have hydrogen sulfite or bisulfite, hypochlorite, chlorite, chlorate for chlorate.
Very catchy mercury one.
Yeah, this is This is another one of those odd ones. So in this case, right, mercury is in the 1+ oxidation state. So let's see if you can name these. I may have to scroll back and forth for y'all. Maybe let's just move them over for a second. So take a couple of minutes. Can you identify where's the polyatomic? Find it on the chart. And then write out the formulas. And don't forget, right, some of them may be variable oxidation states. So keep that in mind, right? Your naming rules apply. Do we find our polyatomics? So what do we get for this first one, K2CR207? You want to go for it since, oh. So I see in the chat potassium chromate. I apologize for the fuzziness. Oh, I think if I zoom in, that'll help. So potassium, it should be dichromate, but I understand it was hard to see that in the chat. And again, right, we just have good old potassium. It's always in the 1+ oxidation state. So we just name our metal and then name our polyatomic of dichromate. So excellent job, chat. What about this next one, MgOH2?
Just magnesium peroxide, or would it be magnesium diperoxide?
Try,
Wait, hydroxide, sorry, I was looking at the wrong one.
no worries. So yes, and I see it in the chat too, so magnesium hydroxide, exactly. So we name our metal. It's always in the 2+ oxidation state. Then we add our hydroxide. So if you look at your chart, hydroxide has a -1 charge on it, and that's why, right, we have 2 of them to balance out that 2+ charge there. And then what about the last one? So we have FeNO3, 3.
Iron nitrate.
So I like that, except what's missing? So remember, iron's one of those variable oxidation states. So we got the nitrate, so let's look at it. So we have nitrate, so this is NO3 with a -1 charge on it. And then there's 3 of them. So what's our oxidation state of iron? So let's see, is that a finger for 3? So 3, so exactly, so we need to write iron 3 nitrate. So we know how many nitrates to put in our formula, right? Because backing it out in reverse. So we know iron 3, okay, that's 3 plus. Then I have my nitrate, and then we can do our little swap trick and get back out our same formula. So any questions on that? So I will print out this chart for you. I think this is my favorite chart. Just because it's the most complete. I was just seeing if there's anything I want to point out. I think that's fine. Oh, kind of smashed through that chapter. So let's do some practice. So see if we can name them. Oh, let's look at 4 for a second because I forgot to cover these. And so we're looking at this. Well, let's just start with this first part. So BeSO3. So how would we name that? I can flip back for polyatomics. Oh my goodness. So chat looks like they're on top of it. I was trying to send chat a polyatomic ion sheet, but I see beryllium sulfite in the chat, so let's just go through that. So sulfite, exactly, so that matches, right, SO3 with a -2 charge. So beryllium sulfite. But then I didn't mention how to name this or what this is. And so all this is sometimes there are compounds that form complexes with water. And so in this case, we want to use some prefixes to name it. So I'm trying to find. Let me, oops.
7-dihydrogen monoxide.
So I'm just going to paste this in the notes. So this tells you the different prefixes. So you could have what's called like a half equivalent. So this would be hemi, and so this would be hemihydrate. So you essentially, right, look at your prefix and then add hydrate to it. So in this case, we're at 7 equivalents of water. So then we look for 7. So that would be hepta. So then we can just name it beryllium sulfite and then heptahydrate.
Could you give an example of the 0.5 and 1.5, like on both 0.5 and 1.5 or 1.5, please?
So, let's see. I guess I'll put it on this page over here. So you could have the formula, so calcium sulfate, and then it would just be indicated by this half H2O. So then you could name this calcium for our metal, sulfate, right, for our SO4, and I just want to point this out so we're all on the same page right now. So write SO4 for sulfate, and then with our half equivalent, so all this means, right, is that for every 2 molecule or ionic compounds of calcium sulfate, right, there's 1 water complex to them. So then we just write hemihydrate there.
And I guess, and how do you pronounce supply?
It'd be Sesky,
Sesky, okay,
and then
that makes sense.
so I've had to admittedly look up a compound. No, that's not correct. You know, admittedly, I've never seen sesquihydrite in like practice. So apparently, for fun facts, there's this pantoprazole sodium sesquihydrite, but I think having 1.5 equivalents is pretty rare. I was trying to find.
Ooh, what's it do?
Oh, apparently there's a potassium carbonate example. What does what do? Sorry.
Oh, nothing on specific chemical.
Oh, yeah, that I don't know. I was just looking at. So apparently there is, this is a much easier example. So apparently there's a potassium carbonate sesquihydrate. Again, I've never seen this in all my years, but we could just write that. So again, potassium, then this CO3 for, where's our carbonate? I'm blind. There it is. So carbonate, so we know that has a -2 charge. So potassium, carbonate, and then sesquihydrate. But like I was saying, so you typically don't see that, but definitely a lot of di, tri, tetra, penta, etc. All right, so let's do a few examples. So try number 1 for sure, 5 and 6. So we'll start with those 3 for now. So take a couple of minutes. Then let me know if you need to see a chart or something. I can flip back and forth. Oh, do you need the polyatomics? Let me know if I need to go back. Flip back for a second. So let's at least start going over them. So what do we get for this one? So what's our polyatomic? Let's start with that.
Sulfate.
So we have sulfate, so let's go. Okay, let's find it on the chart together. So we have sulfate, so a -2 charge. So if this is all, right, -2, and there's 3 of them, so what's our charge on molybdenum? Yeah. So, right, our -2 times 3 is -6, so we need a +6 to balance that, so that's just molybdenum, which I might have misspelled, and then 6 sulfate. So does that make sense? So what about 5 over here? So Fe3, PO42. You can always try to back out your swap trick. Does that match up? This -3? What's this PO4? Do we know?
Phosphate.
So phosphate. I see an answer in the chat too. So we have, right, our PO4. It has a 3- charge on it. There are 2 of them, so -3 times 2 is -6 with 3 iron, so that would have to be 2+. So again, excellent job, chat. So iron 2 phosphate. And then what about this last one here? Kind of try to break it down. So what's our cation? Go back to our chart. I also gave a hint, this is our 1 positive. Oh, is it not? Oh, there it is. So I see it in the chat, right? We have ammonium. So that's one of our few, or if not only, right, polyatomic cations. There's our NH4 plus. Oops. So there's ammonium. So we can just name, right, that polyatomic cation. And then do we recognize what the anion is? So it does have carbon. So which one did I warn y'all? It's one of the ones I pointed out. It always. And at least, so you kind of have, right, your carbon-based ones over here. So is it acetate, oxalate, tartrate, or benzoate? Yep, so it's good old acetate, so C2H3O2. So right, that matches C2H3O2. Remember, it could be written in other forms as well, so now we can just write our ending part of acetate. And so that's just our formula there, ammonium acetate. All right, let's go ahead and end there today so I don't run over like I did last time. And then we do have lab at 7, so I don't know if some of you will run out and grab some food. Otherwise, I will see y'all at 7 for lab 2. And like I said, lab 2 has been posted on Gradescope, so you could turn it in there, and then I'll hang around on the chat in case there are any questions before I sign off.
So the main things I was looking at was 1, the chemical compound you had showed as the example, and also 2, more just how reactivity works for organic molecules, like, you know, how you can tell if a molecule is organic, or the reactivity of a compound, essentially.
Sorry, what are you talking about?
Oh, I was just saying that's what I was looking at, is mainly how to tell the reactivity of a compound. It seems to be based on the primary, secondary, and tertiary carbons.
I think you're kind of going off track, because that's more like OCHEM. So that's like you're right, but that's not related at all to what we're talking about.
Oh, I'm sorry.
Yeah.
I got on a tangent. I apologize.
Homework. Oh, for this week? Yeah, you can throw it in that pile too. So I'll hang around on stream another minute or so in case there are questions. So thanks again, chat, for your participation. See ya.
Oh. Why would you want to watch that?
I haven't seen any of the Fantastic Beasts yet, but I know I'm behind. But then I heard some people complain about this latest one just because they said it didn't feel like English enough, because I guess it was filmed by Hollywood or something. I don't know.
What, did it feel British enough?
Yeah, I mean, they're like, it didn't feel like it was.
It doesn't take place in England.
Man, I stopped following Harry Potter